Hello friends, in this lecture, we are going to learn about quantum free electron model proposed by Sommerfeld. Before we start the lecture, let us revise the plan of the course. So, we are doing free and independent electron gas model by ignoring electron ion and electron Coulomb interaction. This can explain the properties of the metals to some extent. We already have done classical free electron gas model proposed by Trude. Now we are going to do quantum free electron gas model proposed by Sommerfeld. Schrödinger equation for free particles is given by this. Now, the time-independent Schrödinger equation for free particles can be solved using two different types of boundary conditions: fixed boundary condition and periodic boundary condition. In case of fixed boundary condition, the eigenfunctions must vanish at the boundary. As a result, eigenfunctions are standing wave solutions. However, charge and energy transport by electrons is more conveniently described by traveling waves. This can be achieved by using a periodic boundary condition. In case of fixed boundary condition, particles get reflected from the boundary, causing momentum to change sign. In case of periodic boundary condition, particles leaves the box from one end and simultaneously re-enters from the other end, conserving the momentum. Note that psi and x are not eigenfunctions of the momentum operator in case of fixed boundary condition. So this is the eigenfunction and this is the momentum operator. And now you see that if you take a derivative of this, then this becomes cosine, correct? So that means the eigenfunctions are not the eigenfunction of momentum operator. However, if you take the solution for the periodic boundary condition, the eigenfunction for the periodic boundary condition, then if you take a derivative of this, then this psi of kx, this is actually an eigenfunction of the momentum operator with eigenvalue h bar k. Now, the other things are the following. The allowed values of k for the fixed boundary condition are given by this, whereas the allowed values for k are for the periodic boundary condition are given by this. And then we have the energy eigenvalues for fixed boundary condition, and we have the energy eigenvalues for the periodic boundary conditions. And then the in case of fixed boundary condition, we get like standing wave solutions where k is not momentum. In case of periodic boundary condition, we have traveling wave solution where h bar k is the momentum. So far, we have been discussing in one dimension. Let us make a transition from 1D to 3D. We consider a cubic box of volume V. So, electrons are confined in this cubic box of volume V. All the sides are of length equal to L. The time-independent Schrödinger equation for free electron in case of a 3D box is given by this. Now, this is the divergence operator. So we are going to work in Cartesian coordinates. In Cartesian coordinate, the divergence operator is given by d2 dx square plus d2 dy square plus d2 dz square. Now what we do is that we can do a separation of variables. And we can just write the wave function as a function of x, a function of y, and a function of z. Now, if we put these two terms, like if we take the divergence operator in Cartesian coordinates and we just replace this wave function in this equation, then after separation of the variables, we can write the three equations. H cross square by 2m d2x dx square is equals to ex times x minus h cross square by 2m d2y dy square is equals to ey times y and minus h cross square by 2m d2z dz square is equals to ez times z. And then, of course, ex plus ey plus ez is equals to LHC. Now you see, we got like three time independent Schrodinger equations in one dimension. Now let us try to solve one of them, and then this is again like as we did before. We just write this equation, say d2x dx square is equals to minus kx square times x square k of x square is equals to minus 2m ex, sorry, this is like plus 2m ex divided by h cross square. And then the solution for this equation is, since we are using now periodic boundary condition, the solution is given by x of x is equals to 1 by square root of L e power I kx x. And similarly, for the other part, we can just write y of y is equals to 1 by root over of L e power I ky y, and z of z is equals to 1 by root over of L e power I kz z. Now we can combine these three, and psi x y z we can write it as, so if we combine, this will become like L and L, so that is like 1 by square root of L cube, so which is 1 by square root of V. And then if you combine these three terms, we can just write it as e power I k dot r. So if we are using periodic boundary condition, then this is the eigen function. So we have solved for the eigen functions for free particles in a cubic box of volume V. Now let us focus on the periodic boundary condition. If this is a 1D problem, we would write the periodic boundary condition as x of x plus L is equals to x of x, y of y plus L is equals to y of y, and z of z plus L is equals to Z of Z. Note the difference. In case of fixed boundary condition, the wave function must go to 0 at the box edges, but that is not required if we are using periodic boundary condition, and these are the boundary conditions in case we are using the periodic boundary. In case of 3D, we can combine and then write the boundary conditions like this. So psi x plus L yz is equals to psi x yz. So this is along x. The boundary condition along y can be written as psi x comma y plus L comma z is equals to psi x y z, and boundary condition along z can be written as psi x y z plus L is equals to psi x y z. Now let us apply and see what do we get. So we have psi of x plus L y z is equals to 1 by square root of v e power I kx times x plus L into e power I ky y. So what we are applying is this one, okay, and e power I kz z, and then this must be equated to 1 by square root of v e power I kxx e power I ky y e power I kz. Okay, and now if you cancel these terms as well as the term e power I kxx, that also get cancelled. So that means we are left with this. Okay, e power I kx times x is equals to 1. Similarly, if we take the boundary condition along y and along z, then we will get e power I ky times L is equals to 1 and e power I kz times L equal to 1. And we know that 1 in the in the exponential form, we can just express 1 as this e power I 2 pi n, where n is some integer. So that implies that we have kx times L, this must be equal to 2 pi nx and so on. And in that case, the allowed values of k are kx is equals to 2 pi nx by L, ky equal to 2 pi ny by L, and kz equal to 2 pi nz by L, where nx, ny, nz are integers. That means this can be like positive integers, negative integers, as well as 0. We can also get the eigenvalues like E of k is equals to h cross square k square by 2m. That is equal to h cross square by 2m kx square plus ky square plus kz square. What is the physical significance of this vector k? There are 2 points. The first one is h bar k is momentum. For example, if we take the eigenfunctions, then we see that these eigenfunctions are also the eigenfunctions of the momentum operator with the eigenvalue h bar k. So that means electrons in state this has a definite momentum equal to h bar k. And we can find the corresponding velocity. V is equals to h bar k by m. So if I just divide by m, then we get the velocity. And then the energy can be expressed in a familiar classical form. E is equals to, we know that this is the energy eigenvalue h cross square k square by 2m. And once we identify h cross k as the momentum, then we can write the energy is equals to p square by 2m. This is the classical form of kinetic energy. Now, k can also be related to the de Broglie wavelength. So we have this wave particle duality, and then if lambda is the de Broglie wavelength, then we know that, then we can actually show that this k and lambda, they are related by this equation. Before I go to the next part, let us summarize what we have done so far. So we have taken free electron in a cubic box of volume B. And then this is the time independent Schrodinger equation. And so since we are doing it in 3D, so del square, this is the divergence operator. And then the eigenfunctions for this time independent Schrodinger equation can be found to be this. And then the energy eigenvalues are h cross square k square divided by 2m. And now if we apply periodic boundary condition in all the three directions, then the allowed values of k are given by this. So we have like kx, ky, and kz. And here nx, ny, nz are integers. So that means they can take values like this, all the positive and negative values as well as 0. And what is the physical significance of k? So e power I k dot r is the eigenfunction of momentum operator with eigenvalue h bar k. And like wave particle duality, the de Broglie wavelength is related to k by this equation. Let us now construct a space with the allowed values of kx, ky, and kz, and using like kx, ky, and kz as three mutually perpendicular axes. This is known as a K space. For the purpose of illustration, I am going to use 2D. So you see that we can take this kx and ky, these are the two axes, and then we have these allowed values. So for example, we can take a point where nx is equal to 0, ny equal to 0. So that is my 0, 0 point. So that is my 0, 0 point in K space, this one. Then we can take nx equal to 1, ny equal to 0. That means this is my 1, 0 point. So this is the 1, 0 point in the K space. And similarly, we can do nx equal to 1, ny equal to 1, and that will become the 1, 1 point, and so on. Note that each point in the K space represents a stationary state. For example, 0, 0, this represents the ground state, 1, 0 represents the first excited state, and so on. Now, we can also say that each point in K space corresponds to one energy level. So for example, the 0, 0 represents the ground state energy, 1, 0 represents the first excited state energy, and so on. So now what we notice here is that each K point occupies some volume in the K space, which is shown by this blue shaded region. It's very simple. We just join this point 0 to 0, 0 and 1, 0, and then just draw this perpendicular. So this is the perpendicular bisector. And similarly, we join this point 0, 0 and 0, 1, and this is the perpendicular bisector, and so on. So that means the blue shaded region, this is some volume or some area which is unique to this point. So for example, the first point is say this is like 0, 0, and the second point, if I put n equal to nx equal to 1, right, the second point is 2 pi by L 0, and the third point is 2 pi by L 2 pi by L, and so on. So that means the area, right, each side of the square has a length of 2 pi by L. So that means the area occupied by each point is 4 pi by L square. And if we consider 3D, the volume occupied will be 2 pi by L whole cube, that is equal to 8 pi cube by V. So this is the volume occupied by a point in the K space. Now let us come back to this interpretation. Okay. So now Each point in the K space will correspond to one energy level, and energy values are given by this. And then you see that the energy levels can be degenerate. Degenerate means they can have same energy. For example, energy will be same for different allowed K values. So this is one allowed K value, plus minus, say 2 pi by L 0 0, right? So this is one allowed K value. The energy for this will be same as energy for some other set of allowed K values, like 0, 2 pi by L 0, or like 0 0 2 pi by L. Okay, so that means you see that there are, like, if I just consider this plus and minus sign separately, there are like 6 allowed K values, and all of them have same energies. Now we already have found the volume occupied by a point in K space. Now if we invert the volume occupied by a point in K space, we get the K space density of energy level. That is the number of energy levels permitted per unit volume of the K space. We will see that this is the most useful information we get as a consequence of quantization of K values. Now, let us fill the energy levels with electrons. Since electrons are fermions, they must obey Pauli exclusion principle. Remember that each point in K space corresponds to an energy level. Thus, filling of energy level is same as filling of K space with electrons. So let us see some example. So let's fill the ground state with electrons. So we will put like 2 electrons in the ground state, and this is same as putting 2 electrons in this box in K space. Similarly, the first excited states, there are 4 of them, because we have like 1 0, and then we have -1 0, we have 0 1, and we have 0 -1. So now if we fill the first excited states with 8 electrons, that is same as filling these boxes with 2 electrons. Since each K point occupies a fixed volume, certain amount of volume in K space is related to the number of electrons. Now, let us take a sphere with origin at 0 0 0. So you see, this is the origin. And then calculate the number of K points inside this sphere, right? You see this red circle. Since I am showing the sphere in 2D, this looks like a circle. So this is the sphere with some radius. And then we have to calculate the number of K points inside the sphere. Now, the radius of the sphere is called Kf, the Fermi wave vector. And the reason behind the name will become clear in next couple of slides. So far, I have only shown a 2D figure. The circle of radius Kf, so far I have shown this circle. This circle will become a sphere of radius Kf in case of 3D. All the states inside the sphere of radius Kf are filled, and all the states outside the radius Kf, they are unoccupied. Thus, Fermi surface is the surface separating the occupied and unoccupied states. Fermi surface is spherical for free electrons. This is because the energy is given by this equation, right? The energy eigenvalues are given by this equation, and This is an equation of a sphere in K space for a given energy EF. Okay, so we can just call this energy. So this line corresponds to some constant energy, and we can call this Fermi energy. In general, Fermi surface need not be spherical. This point will be discussed in detail later. So far, we have chosen Fermi wave vector in ad hoc manner. Now the question is Fermi wave vector kf related to some measurable quantity? To find this out, let us calculate the number of states or number of energy levels within the Fermi sphere with radius kf. So if the radius is kf, then volume of K space within radius kf is 4/3 pi kf cube. Okay. Now volume occupied by 1 K point. Volume occupied by 1 K point. Correct. So this is given by 8 pi cube divided by P. Thus, we can find out the number of K points, correct? Number of K points within the sphere. This is given by 4/3 pi kf cube into, so 1 by delta k is v by 8 pi cube. So thus, this is the number of K points within the Fermi sphere of radius kf. This is given by this. According to Pauli's exclusion principle, each state can hold up to 2 electrons. So thus, the total number of electrons in the sample or in the metal, if it is equal to n, then n must be equal to 2 times this number, right? The number of states, correct? So 2 times number of states, and then this number is equal to this. Now, what we do is that we just rearrange the term and note that n by v, right? So if I just bring this v to the denominator, then n by v, this is equals to kf cube divided by 3 pi square. Correct? But what is n by v? N by v is the number of electrons per unit volume. Correct? So that is n is equals to electron density. Okay, so that means the Fermi wave vector kf, this is equal to 3 pi square n to the power 1 by 3. And we can also express this with this expression, 3.63 divided by Rs divided by A naught. This number Rs by A naught, this is a number which is like between 2 and 3 for most of the metals. So if we just put this number, then we see that this kf, the magnitude of kf turns out to be of the order of 1 angstrom inverse. Okay, so what we have achieved here is that we have finally related the wave vector, or rather the Fermi wave vector, to a measurable quantity n, which is the free electron density. We can relate several quantities to the Fermi surface. For example, we can define something called a Fermi energy, which is the energy of the highest occupied energy level. And then this Fermi energy turns out to be a number which is of this magnitude 1 to 10 electron volt for most of the metals. Remember that we are still at T equal to 0 Kelvin, right? So classically the kinetic energy should be 0, but we see that quantum mechanically this turns out to be a number which is lying between 1 to 10 electron volt. Now, if we take the Fermi energy and divide it by Boltzmann constant, we can define some temperature, and that we call as Fermi temperature. And this turns out to be a number which is huge, which is like 10 power 4 Kelvin, right? So, to match the kinetic energy of a quantum gas at T equal to 0, the temperature of classical gas should be of the order of 10 power 4 Kelvin. Now we can also define Fermi velocity, which is the velocity of the most energetic electrons. How do we do that? So we just Vf is equals to this. We just define something called Fermi momentum, and then Fermi momentum is h cross times kf divided by mass, right? That will be the Vf, and then that turns out to be a number which is of the order of 10 power 8 centimeter per second. Now, at 0 Kelvin, of course, the velocity will be 0. But if you measure at room temperature, then for classical electrons, this turns out to be a number which is of the order of 10 power 7 centimeter per second. But in case of quantum free electron gas, even at 0 Kelvin, this is 10 times higher than the classical electrons at room temperature. So this implies that, so if we try to calculate the kinetic energy, which is the square of the velocity, this implies that quantum electrons are 100 times energetic than classical electrons. Remember that all these are the consequences of Pauli's exclusion principle. Since we can put only 2 electrons per energy level, and the solid has typically 10 power 23 of them, electrons close to the Fermi level have very high energy. Before I finish the lecture, let me show some Fermi surface related parameters for selected metals. For example, the electron density turns out to be a number which is like 10 power 22 per centimeter cube. The Fermi wave vector turns out to be a number which is of the order of 10 power 8 centimeter inverse. The Fermi velocity turns out to be a number which is of the order of 10 power 8 centimeter per second. And then the Fermi energy, this lies between like 1 and 10 electron volt roughly. And Fermi temperature lies, or Fermi temperature is of the order of 10 power 4 Kelvin. In the next lecture, we shall derive various thermodynamics properties of metals. Thank you.